Yes.
Am I too loud?
No. No, you're good.
I'm good. For office hours, it's Monday, Tuesday, Wednesday. It will be 2:30 to 3:30. I already sent out the link for the Zoom meeting. But I appreciate if you drop me an email ahead of time, because if nobody is planning to call, I am trying to not to just start there and just stare at the screen for 1 hour. Okay, so if you plan to ask questions, just send me an email ahead of time. So any other questions before we actually start? Hope everybody is doing all right. Try to be safe. It's important. It's important for you to do your part in terms of social distancing. You guys are young. If you get the virus, the likelihood that you will survive and do okay. But if the transmission is going at this rate, it's really exponential growth currently. It's going to be very bad for the whole country, especially for old people like me. So please be nice to me, okay?
Stay healthy.
Yeah. Don't interact with that many people. Okay?
How come everyone has their video off?
Yeah. Okay, so we are doing 4.9 today, section 4.9. I actually, in each of my 3 other classes, I got someone volunteer to record the lectures and post it on discussion in campus. I don't know whether you guys care or we have a volunteer for this class. Okay, it's up to you guys to figure it out. You are doing it again, Hans? Oh, you're doing it for the other class already. You are so nice. Oh, you are so nice. Yeah, thank you so much. Oh, by the way, I forgot to mention that Joe Sway was really nice. He posted something on the under discussion. Excuse me. About he posted something on discussion about how to access the old homework. Because some of you want to look at the old homework, right?
Mm-hmm.
So if you go to campus under discussion, he has step by step with screenshots and everything. It was really nice of him. Okay.
Thank you.
Yeah, is Joshua here? Doesn't look like he's here. Okay, so we will start.
Is there a reason why everyone has their camera off?
So that we're not distracted. Just so that we see his visual.
Okay, can I turn off mine too then?
Yeah.
Yeah.
Mhm.
Oh, you have a new power. It's an apple. Okay, we are doing section 4.9 today. Okay, section 4.9. Markov chain. So this is an application of the linear algebra stuff that we do. Okay, so we are starting to do some applications now. It's probably a little bit better, not as painful as before. Less concept, a little bit more calculation. I start out with an example. This is about population migration, okay, between city and suburb. Those are probabilities. Those numbers are probabilities. Okay. So this is a probability. If you live in a city, there's some chance that you actually will go to the suburb on the next time unit. Okay. Maybe next year. Okay. This year you live in the city. Next year you will be 95% chance you stay in the city. 5% chance you go to the suburb. If you are at the suburb, 3% chance you will live in the city, move into the city. 97% chance you stay. Okay. So this initially 60% of the people in the city, 40% in the suburb. So what happened after 1 year? Okay, what happened after 1 year? Let's see whether I can convince you. Okay, after 1 year, how many will be in the city? You start out with 60% in the city, originally 60% here. Okay, and you have 95% chance of staying, plus those who actually migrate from the suburb to the city. Okay, the suburb you originally have 40%. The chance it going there is 0.03. So this is after 1 year. Do you guys agree with this equation? I want you to think about that. It's probabilities. A lot of you are not familiar with it. Look at that and tell me if you have issue with this equation. This is after 1 year. Yes, no, okay.
Yeah.
Other people, is it okay? I'm gonna assume it's okay. If you don't speak up. Some of you cannot speak up because you have to do chat, right? Because you don't have a because you don't have a microphone or something?
Well, a lot of us are muted just so that you can't hear the background noise in our places.
Okay, so I actually don't really mind if you unmute it. Okay. Or if you want to actually let me know that you are, I mean, you understand what I say, the concept.
Well, are you looking at the chat? Do you have the chat up?
It's kind of difficult. I have it out. I have it up now.
Okay, so you would prefer for us to answer vocally?
Yeah, that would be easier because I mean I'm at the whiteboard and the chat is kind of far away. Is it okay, Anna?
I'll go along.
Okay. All right. So this is good. This equation is good.
Yeah.
So how about maybe you can tell me the equation for the suburb? For the suburbs, sorry, we have some background noise there. I apologize.
Sorry.
It's okay. Because I'm doing this in the about 10, 12 feet from the kitchen. Okay, so what's the equation for the suburb after 1 year? Can you guys tell me?
0.4 times 0.97.
Okay, I'm going to write the form 4 here, okay? Plus what?
0.6.
Originally here, 0.6 times.
0.01.
Is it like this?
Yeah.
You guys all good?
For the city, it's 0.6 times 0.95.
Mm-hmm.
Okay.
Yeah. So initially it's this. Now this x naught is a state now, x naught, okay? This is not the coordinate, okay? X naught itself has 2 entries, 0.6 and 0.4. This is the initial value for x naught. This is the state of the system. Initial state. Okay, after 1 year, you have the next one. So each state is a vector. So x naught itself is a vector. X1 is another vector. Now this x1 is this guy, but this guy can be written in some matrix form. What is that matrix there? Also, I write there. 0.95,
0.05.
0.05, 0.03, 0.97. Okay, and this is matrix A. Sorry, I'm going to use P, okay? Because my notes use P. P stands for probability matrix. This is a probability matrix. It's also called a stochastic matrix. Okay. It has the property that sum of each column is equal to 1. And also all entries definitely equal to 0. Okay. Because those are probability, you cannot have negative probability. Okay. So what do you think is x2? How is x2 related to x1? It's another year, right? After another year. Can you see this is p times x1? Yes or no? Is it okay? Do you guys agree x2 is p times x1?
Yes.
Wait, no. Why?
Okay. No, Eva. So it's the same argument, Eva. Just repeat the argument. Because x1 now, instead of 60 and 40, you have some other numbers.
Oh,
It's the same argument.
okay.
Exactly the same argument.
Okay.
Is x1 x naught?
Yeah? Somebody say something?
Is x1 what used to be x naught or no?
No, x1 is p times x naught.
Yeah, x1 is p times x naught. Oh, I didn't write that. I write that somewhere. Oh, sorry. I should have written it there.
Okay.
Thank you. X1 is p times x naught, right? X2. X1 is this is p times x naught. Okay. X2 is p times x1. And so on. X3 is p times x2. Now another way to write this guy is actually p squared x naught. This one is p cubed x naught. Is it okay?
Yeah.
So in general, xk plus 1, the state after k plus 1 here is p times xk, or xk is p to the power k x naught. All these equations are pretty intuitive. Is it okay?
Yeah, this is good.
Okay. This is an example of a Markov chain. Okay. I need to write down the definition of Markov chain. This is bad. I don't have enough space. Let me see how I organize it.
Professor, since we already know that Hans is going to be recording this, you can probably erase some of this.
Okay. Yeah, I'm gonna do that. Yeah, thank you. I need probably to do a better job of maybe writing a little bit smaller. Okay.
I would have to agree with Hans.
Okay. Okay. Definition of Markov chain. Probability vector just means that sum of entries is equal to 1. Okay, and also each entry is bigger than or equal to 0. Okay, so those are probabilities. Together with a stochastic matrix. Okay, so that's the definition of Markov chain. Okay. Has a lot of useful examples, useful applications. So in this case, this is a two-state system. We have two states. Okay. Google's PageRank algorithm, each web page is one state. How many web pages are there out there? Billions. So they have a graph which has billions of these boxes connected by some probability, which is, if you're in one page, what is the chance to go to these other pages? Okay, how do they determine that? Depends on how things are like reference and so on. Okay, if this one reference another web page, then they have some probability of going back and forth. So they have a Markov chain with a lot of states in the order of billions. And they use the theory to basically rank the pages.
Wait, Professor,
Yes.
I thought it's not if you're on like one page how likely you are to go to the next, but like when you type in something to Google, so is it like it has that whatever you type in and that's a box and then the pages are other boxes?
They actually it's the Markov chain. They have all these probabilities, and they use it to solve this thing called. They basically try to see which pages are more important. Okay. The importance of the page is related to a score, which is called the steady state distribution, which we are going to talk about next. Okay. All right. So based on that steady state distribution, they will know which page is more important, and based on that, they rank it. Roughly speaking.
Okay.
Roughly speaking. So we have the concept of steady state distribution, which we're going to talk about now. Okay. So in this example that we have, okay, this guy actually, this is what we're interested in. We're interested in limit xk as k goes to infinity. This is what we are interested in. Okay. So how do we do that? We will revisit this type of problem a little bit later, but for now, you just have to kind of trust me on some of the results. Okay, I won't be able to prove everything. Okay. So if this guy is going to be some distribution, okay, let's say this guy is going to be equal to Q. Okay, this guy is equal to Q. What does that mean? That means let's look at this. Okay. So if you take the limit on both of this, now this one will be Q, is that right? The other side is PQ. You guys understand what I did? I'm using this relationship, okay, to show you that as k go to infinity, Q is equal to P times Q.
Okay.
And Q is called the stationary distribution. How is it going?
So the limit as of x of sub k plus 1 is the same as the limit of limit of x sub k?
Yeah. Yes.
how come? Like,
How come? How come?
oh, because it doesn't not matter as k goes to infinity. Is that?
Yeah, k is going to infinity anyway.
Okay. Okay.
Okay. Oh, sorry, this is not x go to infinity, it's k go to infinity. As k go to infinity, k plus 1 also go to infinity, right?
Okay. Yeah.
Right? So it's the same thing. Is it all right?
Yeah.
So essentially, I say that I can put the limit in here.
Okay.
It's okay, right?
Yeah.
Okay, so Q is called the stationary distribution. Let's try to find Q for this example. Okay? We want the stationary distribution. Eventually, it will settle on that state. Okay? How do I solve it for this example? For our example, it will be like this. It will be P is equal to this guy, right? We need to solve PQ equal to Q. What is P? P is did I write down the matrix? I wrote down the matrix, but I erased it, right? Is it like this? This is my P, right? Yes?
Yeah.
That's right.
We want to solve this. Okay? So this is the same as this Q here. This Q here. I'm going to write it as IQ. I is the identity matrix. So that, so this is P. So actually I have P minus I times Q equal to Q. That's what I want. What is P minus I? P minus I, subtract 1, right? On the diagonal. Okay, do you guys follow? Subtract 1, this is negative.
On the second row, it's
Oh, this is mess up. Mess up. Is it better? I fix it.
I thought for the second equation, is it P minus I times Q equals 0?
Oh yeah. Thank you. I'm so bad. Okay, thank you, Eva. Okay, is it good now? Are you guys following?
Whoa.
Yes? Did somebody say yes? Okay. All right, we just need to solve this. Okay. Solving this is probably not too bad. Okay, we are going to solve that. What do we do? RLEF, right? RLEF, what do we do? So these guys are going to be gone. Essentially, it's minus 5, 3, 0, 0, 0, 0. Is it okay? Those two rows are basically the same rows. Okay? And I get rid of the decimal. Are there 3 variables? If I want to do, can I get this to be 1? Is it okay? Yes?
Mm-hmm.
Looks good.
Looks good? Oh, this is 1, not -1. Okay, how about this? This is a 1 and that one is negative. Okay, so there's a free variable. So these guys are Q1 and Q2. So Q2 equal to Q2, Q1 equal to what? 3/5 Q2. So Q will be Q2 3/5 1. Is it okay? Now that means this Q can be any scale multiple of this guy. Can be any scale multiple of that. Is it okay? Are you guys still with me?
We're still here.
Okay.
So how did the bottom one come about?
From here. This is a free variable. Q2 equal to Q2, Q1 equal to 3/5.
Oh, okay. Okay. Let's see.
So Q is equal to this. A Q2 is a scalar. I mean, you can scale it any way you like. But I want to scale it so that it's a probability vector. Okay. So this guy, I want the sum of these two to be equal to 1. Okay. So basically, this is any scale factor times, I mean, I can scale this to get rid of the fractions, 3 and 5. Okay. This is some constancy. I just scale the parameter Q2. So I need this to be add to 1, but this one add up to 8. What should we see? To make the entries add up to 1.
Like how did you do that?
Huh?
Why can you just multiply it by a constant?
I multiply the whole thing by a constant. I multiplied this by a constant 5.
Okay.
I'm allowed to do that because this Q2 is just can be anything you want, right?
Mm-hmm.
But I just want to get into integer form so it's easier for me to think about. So I need to choose C equal to 1. What is the value of C I should choose to make the sum of the entry equal to 1 so that I actually get some probability vectors? 3 plus 5 is what?
8.
So 1/8.
3 plus 5 is 8. In order for it to be 1, I have to divide by
8.
So I have to choose C equal to 1/8. Now I have my Q. So after a long time, okay, it will settle on 3/8 of the people will be in the city and 5/8 will be in the suburb. That's what you say. Is it okay?
Mm-hmm.
Any questions so far? Any question?
No.
So here's one result that's useful. By the way, P is a square matrix, okay? In all these cases we are talking about, because P is a square matrix, because in general P look like this. This is from certain state to the other set of state. Okay, for us it's from the city or suburb to the city and suburb. Okay, so the P is always a square matrix. In general, P is n by n. Always has non-trivial solution. How do we know that? It is big. You guys understand what this sentence is saying? What is it trying to say? That means it's saying that PQ equal to Q, you can always solve for it and get some non-trivial solution. Because 0 is going to be a trivial solution. P times 0 is always equal to 0. Okay? Are you guys all right?
Yeah, this is good.
Okay. So why is this the case? PQ equal to Q is the same as P minus I, Q equal to 0. Okay, so you consider this matrix P minus I. Now P minus I sum of all rows. What's the sum of all the rows? Now each column, just look at sum of each column then. Okay? So the sum of each column for P itself, sum of each column is what? It's equal to 1. Equal to 1, right? Because it's a probability matrix. Yes?
Yes.
So P minus I sum of each column is equal to 0. Because I also has a 1 on each column. Okay? Originally, the P has sum of each column equal to 1. P minus I sum of each column will be equal to 0. Because there is a 1 on each column in the identity matrix. Is it okay?
Mm-hmm.
That means for P minus I, sum of all the rows is equal to a row of zeros. Okay? What does that mean? That means the RREF of P minus I has a row of zeros. It's okay? So how many pivots are there? That means number of pivots in P minus I will be less than n, right? Because there will be a row of zeros. The number of pivots is less than n. So that there will be a free variable. When solving P minus I to equal to 0. Okay? So there will be a free variable when solving P minus I equal to 0 because you don't have a pivot on every row, every column. And that's why there will be a non-trivial solution. So it's okay? So you can always find that non-trivial solution. How are we doing?
Good.
Pretty good.
I'm going to erase most of this, okay? I'm erasing. Maybe you guys can tell me how to find the steady state vector. Oh, steady state vector is the same as the stationary vector I talked about. It's a Q, okay? How do we do this? It will be exactly the same way as we did this before. Will be exactly the same way as what we did before. So we just solve one.
P Q equals
Q, I Q equal to 0. So it will be 0.6 minus 1, 0.3, 0.4, 0.7 minus 1, Q equal to 0. This one will be negative 0.4, 0.3, 0.4, negative 0.300. And this guy is going to get you to minus 430,000, which will get you to 1 minus 4 minus 3 over 4. I mean, I did this before on the other one, okay? I'm just trying to give you one more example. So what does it mean? This means that Q2 is, I'm going to write it here. So Q2 is equal to Q2. Q1 is what? What's Q1? Am I going way too fast? I went a little bit fast because this is exactly the same as what we did earlier.
So is it negative 3/4, or I can't really see it?
3/4 Q2.
Negative 3 over 4.
Okay, thanks. Yeah, no, there's just a glare. Thanks.
Okay. It's a glare. Is this better? But it's really dark. I just turned off some light.
No, you can turn the light on. It's I think it's from an outside light. Yeah, it's better with the light on.
Yeah, I think it's better with the light on.
So Q1 then is 3/4.
3/4 Q2, right?
Yeah.
So Q is going to be Q2, 3 over 4 and 1.
Mm-hmm.
We will need to choose Q2 so that this, so you end up with something with the sum of the entries equal to 1. So the easier way to do this is to clear the fraction first. So this one become 3 and 4. So Q need to be what? 3 over 7. Is it okay?
Yes.
Could you explain why you keep putting the C?
I don't really have to. If that confuses you, you can look at it like this. Okay. You can just look at it here. Okay. So we want Q1 plus Q2 is equal to 1. Okay. 3 over 4 Q2 plus Q2 is equal to 1. 7 over 4 Q2 is equal to 1. Q2 is 4 over 7. Okay, so you put 4 over 7 into here. So Q2 is 4/7. So Q1 is what? Q1 is 3/4 times 4/7, which is 3/7. If you prefer, you can do it like this. It's just that here you have a lot of fractions. The other one, because Q2 is anything I can choose whatever I want, right? Q2, I can choose whatever I want. So I can change it to another scale factor and then multiply both of these by 4 to create a fraction. Once I create a fraction, I know easily C has to be 1/7 because the sum of these two is 7. Did I answer your question, Luca?
Yes.
Good.
Thank you.
No problem. Any questions so far up till here?
Okay, so the steady state vector is as the limit goes to infinity, that's what the x vector will end up.
Yeah, steady state vector is the steady state vector is this. Steady state vector. It's actually a limit xk k equal to infinity. Okay, stationary vector. It's actually slightly different. Okay, this is the solution of PQ equal to Q. Okay, they are actually slightly different. Okay, sometimes they are not the same. Most of the time that we are interested in is the same, but under some condition it's not the same. So here's an example. Okay, so let's say P is equal to 0, 1, 1, 0. Okay, so let's say my x0 is 0.6 and 0.4. My x1 will be what? Now this P, when you this guy is P times x0, right? Can you guys multiply this matrix for me? The matrix and the vector. What would this be?
0.4.
What would it be? Actually, multiply this in your head.
0,
That's 0.4.
0.4, 0.6.
It's actually, this matrix is swapping the rows, right? It's swapping these two entries. So what would be x2? x2 will swap it back to this. x3 will be swapping back to 0.4, 0.6. Can you see that it toggle and alternates? Can you see it alternates?
Yeah.
Okay. So for this example, limit. For this particular example, this limit sorry, this limit does not exist. Okay, so there's no steady state vector. But it still have stationary vector. If you try to solve this, okay, if you try to solve this guy, which is P minus IQ equal to 0, you will end up with, because it's 0, 1, 1, 0, subtract 1, you end up with minus 1, 1, 1, minus 1. You guys know what I'm doing? Do you guys know what I'm doing? I'm trying to solve this. P minus I is this guy, and I do the augmented matrix.
Yeah.
So the steady state vector, in this case, this guy you will end up with 1 minus 1, 0, 0, 0, 0. So Q2 is Q2, Q1 is equal to Q2. So the two entries are the same. If the two entries need to be the same and you end up to 1, so my Q is going to be 0.5 and 0.5. So you do have a stationary vector, because if you put 0.5 and 0.5, you keep targeting them, it's still 0.5, 0.5. Okay, but if you start out with something different, then it's not going to, the limit does not exist. Okay, but then in this case, for this example, this guy does not, no stationary vector, no steady state vector, but stationary, this one will be the stationary vector. Okay.
You said usually they're equal though, right?
Yeah,
So,
usually they're equal. There's some technical condition, which I'm going to write down. Okay. Usually they're equal. And if the technical condition is not satisfied, okay, then you can actually just move the matrix a little bit, maybe add some small, very small entries, in small number into each entry, or subtract some small number. That's what they do with the Pagerank algorithm. Okay. If the thing is the matrix does not satisfy the technical condition, you can kind of modify the matrix a little bit to make it satisfy the condition. Okay. Okay, so I am going to write down that technical condition. Okay. Okay, I'm going to write this theorem. I'm not going to be able to prove the theorem. There are books on Markov chains. I mean, it's still, I mean, they have a whole book on this. I mean, it will develop all this theory, but I think it's nice to actually at least touch upon this topic because it's so useful. And it can show you how matrix is being used. Okay, so that is the theorem. But the theorem has this term here called regular stochastic matrix. The other terms I already explained to you what those other terms are.
is it limit as k goes to infinity or x?
Okay.
So, and what does stochastic mean again?
Stochastic means that every column, the sum of every column adds up to 1.
Thanks.
Sum of every column adds up to 1. I have to explain to you what regular means. Okay, I'm going to try to explain to you what regular means. Okay. We'll do some example. Is this matrix regular? This is not regular because you keep doing this. P squared, what's P squared? Guys, do you know what P squared is? P times P. This matrix, when you multiply it with another matrix, is swapping the rows. So if you swap the rows and swap it again.
So we just go back to being 1, 0, 1, 0.
Yeah, 1, 0, 0. Okay. So P cubed will be back to 0, 1, 1, 0, and so on. So is it regular when you keep multiplying by itself? Would it eventually become all positive entries? So the answer is no. Okay.
Wait. Ooh.
Eva?
But it's still positive.
Strictly positive.
Oh, so does that mean non-zero?
Yeah, positive. Even positive means non-zero.
Okay.
Even, I don't even have to emphasize strictly, actually. When you say positive, 0 is not a positive number. If you want to include 0, you say non-negative numbers.
Okay.
So non-negative numbers are the positive number together with 0. Okay?
Yeah.
You just put strictly positive to just emphasize it. I'm not going to test you guys on things regular or not that much. I mean, it's only because there's a technical condition here, okay, for this result, so I have to explain a little bit what regular means. And also there's a couple of homework problems maybe touch upon that. We're not going to use this concept too much later. Is this guy regular? So the easiest way, there's no really good way to figure it out other than just try it out. Let's try to do P squared. You guys help me add this together. Multiply this together, 0.75, is that right? The first entry. The second one is going to be 0.5. The third one is 0.25. The fourth one is 0.5. I'm just doing some arithmetic in my head. You guys know how to multiply two matrices. So from this, we already know it's regular because now P is regular. So because P squared is all positive. Okay. I mean, for this class, the concept of regular matrix is not really that important. It's just that because it's a technical condition, we need to talk about it. But of course, I mean, if you study an entire course on Markov chain, then it becomes important. Any question for this? I'm done with this section, guys. I am going to chapter 5. Unless you have questions.
So in that theorem, it says P has a unique steady state vector Q.
Yeah.
So that means there's only one?
That's only one probability vector. Steady state. That means there's only one free variable. The dimension of the solution space, that means P minus IQ equal to 0. This guy, the solution space for this has dimension 1. That's what you say.
Okay.
This is only one free variable. Okay.
Okay.
But the free variable, usually the free variable is free. You can choose whatever you want. But because of the condition that it's a probability vector, so the entries add up together has to be equal to 1. So that forces you to choose a certain value of that parameter. Okay. But what this unique means that essentially dimension of the null space of P minus I is equal to 1. That's what I say. Okay. I use a lot of terminology here. Okay. I use the terminology we have learned, we have talked about. So we are actually finding the null space of P minus I. And the dimension of that is 1. Any other questions? I mean, I can let you guys ask some more questions. I mean, I don't know. I mean, we only have less than 10 minutes. I mean, it's up to you whether you want me to start the chapter 5 or not. Yes, no? We start chapter 5. How about that?
Okay.
Is it okay?
Yeah.
Okay.
How are we going to do tests?
Huh?
How are we
Are you
going to
gonna
be
do
doing
what?
tests?
Test?
Yeah.
It's going to be online. So make it a lot easier for you guys.
Nice.
It's going to be online. It's going to be open book, open notes, because I have no way to monitor you. Does everybody has a webcam on their laptop?
No, I'm using a desktop.
You're using a desktop. So I cannot see your picture, right?
Yeah.
Okay, that's fine. So I was thinking that if you all have
Did you want to see our pictures? You know, for those of
no,
us.
I want on the test, what I want to do is on the test, you guys all turn the video on. Then I can go to this place. I can just see, I have this thing where I can see every single one of you. You know what I'm saying? So
Yeah.
I have a file of all the pictures. Then I can monitor you whether if you do too much stuff, then must be cheating. If you turn your head 15 degree, to the right or left, then you're cheating. I'm just
Very
kidding.
good. Very good.
I'm just kidding. Okay. So I mean, I can't even do anything basically. Okay. So I will, because some of you don't have webcam. Okay. So I mean, I have no way of. So this is what the tests are going to be done on. I will have find some way of making some online tests, probably just from my MATLAB. Okay. So and then you guys clicking on some stuff and then we'll get a grade. So basically,
Less work for you.
less work for me, maybe a little bit too generous. I mean, to the students in terms of the grades, because now it become a lot easier. Okay, but there's not much I can do though. It's kind of hard. Okay. One way is for you to submit PDFs. Some student can say that I cannot even generate a PDF. Okay, so it's kind of hard. So, but I still want you guys to learn though. Okay, I still want you guys to learn. So all the lectures will continue like this. We'll just keep learning, but the grading may become harder. I mean, harder in the sense of harder to make it fair. Harder to make it fair. So we may become a little bit generous. Any other questions? That's what the plan is. You guys have any other good suggestions? Just no finals, no exams, just everybody get A?
Yeah.
That sounds great.
It doesn't affect you, Anna. You have auditing.
I know, right? Yeah.
It doesn't even affect you. Yeah, that's what I mean, I haven't really figured out stuff that much. I'm doing this, I'm trying this on another class first. But the different classes are different, so it's hard to tell. The pre-calculus class is easier to do it this way because the questions are simpler. But even this class is actually not too bad because there's not much calculation, not a lot of calculation. But for differential equation, it's harder because they calculate 2 pages of stuff and end up with one answer. And it's kind of hard to judge it by just looking at the answer.
Do you think we're going to be online for the rest of the semester?
I would certainly think so. It's not official,
It looks that way.
but I think it's going to be that way, and it might be good to do it that way because of all this exponential growth of the number of infections. I think we need to do that because we need to really play safe, because if we don't do anything, at the end, about 80%, probably about 70 to 80% of the population will be infected.
I feel like the semester's fate was sealed once the shelter in place was put in.
Sealed in the sense that
Sealed in the sense that we're going to be like online for the rest of the semester. I don't see a world where we go back to physical.
Yeah, I think we are going to be online for the rest of the semester. I'm just hoping that, I mean, with this current setup we have, because Zoom is very good, okay? It works pretty well as far as I'm concerned. I mean, I have never used it before, and then was able to just with a little bit of help and set it up. Even not that much help. I mean, I went to this get help at Kenyatta, and I mean, we set it up in like less than about half an hour, and it's working out really well. I mean, so I'm still trying to teach like this, the same style as what I have been teaching before, essentially. I don't think the style has changed. Okay.
Did you already have the whiteboard set up, or did you have to hang it up?
I have to take down my picture and bought a whiteboard for $55.
Okay.
Which may or may not probably won't be reimbursed. So if you guys are nice, each of you should give me $1.
Hey, that's a tax write-off.
Oh my gosh.
That is not a tax write-off for me.
It can be.
I cannot write it off like that. Or you get donation, you can. But I mean, I don't know. Donation to a teacher. So the board is actually hang a little bit too low, but I don't want to have extra holes on my wall
Okay.
because I'm using the same nail for my picture.
Okay.
So that's why it's slightly low. I mean, so I just took the picture out and then put this on.
So are you in your dining room?
Huh?
So what room is it?
This is my breakfast nook.
Okay.
It's a breakfast nook, but we usually eat lunch and dinner also here. So we set up another table for lunch. But dinner we'll eat here. In the breakfast we eat here.
Do you have any pets?
Do I have any pets?
Yeah.
No. I used to have a dog. I'm gonna just move this. Maybe you can see the picture. Do you see do you see the picture of my dog?
Yes.
Aww.
Do you see the picture?
Yeah.
Can you see it?
Yeah.
That was my pet called Riley. She passed away in 7 years ago.
Oh.
Yeah, it's a golden retriever. Yeah. Okay, so anything else? Yeah, so this semester I think will be done like this, and is the Zoom, is it working out for you guys?
Yeah, this worked out well.
Yeah.
Yeah, I think it's okay. I mean, it's much better than I think. Okay.
It's a little depressing that we can't see each other, or I guess some people don't have webcams, but
Yeah. I mean, if you guys want to all turn on your picture, it's okay. I just go to this because I can just go to this particular there is a way to do this. Is called instead of speaker wheel, it's called, what's it called? It's called I have speaker wheel.
Gallery view.
Gallery wheel, yeah. So if you want to turn on gallery view, I mean, it's not I can see all of you, but the picture is small. The picture is going to be small, so it's not like everybody. I just see your whole big head, right? So the gallery view, if you want to turn on your video, that's okay with me. Yeah, then I can actually see you.
Oh, everyone's muted.
Everyone is muted.
Yeah.
So it's only Anna and Eva. Well, how about the other people?
That's because we're the chatty
You
ones.
just talk. You can toggle it on and off. That's why.
I can toggle you on and off.
I can manually. So in case I have loud people in the background, you guys don't have to hear that.
Oh, I see. Okay, I think that's it for today. And
Okay.
next week we are going to do 5.1. Okay, eigenvalues and eigenvectors.
Okay.
Okay.
Cool.
Thank you, Professor.
Bye.
Thank you.
Bye.
Thank you.
Have a nice day, Professor.
Okay. Stay safe. Okay.
You too.
Professor.
Yeah, we need your help to stop this virus. So don't interact with people, because you guys, if you get the virus, you guys will recover really easily. But for the old people like me, so please stay away from people, just so that to decrease the transmission rate, so you can save my life like that. Okay.
If only my work would see it that way.
Oh, really? You still have to go to work?
Yeah, I work at Whole Foods.
Oh shoot.
Yeah, that's what I've been thinking, is all the people in retail and all the people in the grocery stores are really on the front line.
Yeah, I work in a literal petri dish. Most of the customers that come through are disgusting.
Oh.
Like they don't pick up their trash from their carts, stuff like that. But that's not something we need to get into now.
Right.
So maybe you can wear a mask if you have one.
Oh yeah, my work provides masks and gloves and stuff like that, so I'm good.
The mask, I think, even though they say that it's not useful, I think it's still somewhat useful. I mean, especially if you interact with so many customers. Yeah. So I think if everybody do their part and just don't interact, then we can probably stop this thing.
Mm-hmm.
Yeah, because it's exponential growth or decay, depends on the base. If the base is A, if A is bigger than 1, which is what's happening now, we need to get the A to be less than 1. Then it will stop.
Yeah.
Okay, I'll see you guys. Okay.
Have a nice day.
Yeah. Bye.